Swayam Prabha. Digital India. Educated India.
Hello everybody, welcome to this course on data science, and in today's session we are going to cover descriptive statistics. Statistics as a science provides useful measures whenever there are uncertainties in the data. We will look at some of the measures and how we can use those measures to make better sense and meaning out of the data that we have. The data we normally encounter looks something like this. This is a normal spreadsheet, and this data is related to used cars. So the kind of price that gets quoted for a used car, depending on the kind of vehicle type, whether it's a limousine, SUV, bus, etc. The year of registration, which indicates what is the age of the car, the gearbox type, whether it's a manual type or automatic, the power output of the engine, the number of kilometers that the vehicle has run, the type of fuel that it gets used, the brand, which is an important component of a value of a particular car, and whether there is any damage to the car. So we normally encounter data. This is just a snapshot of a data which has about 43,500 rows. So there are 43,500 cars for which we have information on all these variables. As we clearly can see, it's very difficult to get a meaning or a sense out of this data by just looking at this data. So statistics helps us understand the nature of the data that we have in a far more succinct format. So the purpose of statistics is threefold. One is to describe or summarize a situation, a phenomena, or a process. So we want to understand what kind of traffic flows through a particular junction. We want to understand, let's say, a chemical process where what kind of temperatures and pressures are operating at different points in time. Or it could be a social process as to what kind of improvements happen when education is provided to people. So if you have data on any of these situations, statistics helps you describe it in a very succinct format, which is understandable with a common knowledge and a common terminology to be used across different people. So all this goes under descriptive statistics, and this is what we would be covering mainly in today's session. The two other purposes are B is to infer certain conclusions about a population from samples, because it's not possible always to get all data related to a particular phenomena or a process. So you probably look at snapshots of data from the process or a phenomena. So let's say you are trying to find out the traffic count. You are not going to be sitting there through the year. You probably are going to choose certain periods of time, sit there to count the traffic that flows through. Or when it comes to used cars, so I'm going to get data from, let's say, about 43,000 people. But that does not completely describe the universe of used cars that are being put to sale. So you have only a sample of data, and you have certain measures that's coming out of the sample of data, and you want to understand whether you can generalize these summarizations to the population. So that is the inferential statistics that requires a certain understanding of probabilities and probability distributions. We will cover that in a subsequent session. The third important use that statistics is put to is really when you have n number of variables and you have certain characteristics that you can easily measure, and there are certain characteristics that are difficult to measure. So using the characteristics that are easy to measure and that are visible, can we predict what those other characteristics values would be? In the example that we looked at, which is the used car, if I know that the next car that comes in is a limousine with a particular 150 power PS and which is run about 150,000 kilometers, can we predict what the price of that car should be? So essentially we are saying we know certain visible characteristics and we want to understand certain characteristics and compute certain characteristics. So it's to predict a particular variable that a particular variable, the value a particular variable would take if you know certain other variables. Now that's predictive analysis. A lot of statistical modeling and tools in that area are designed to serve this purpose of statistics. So now let's hone in on descriptive statistics. And why do we need descriptive statistics? There are many purposes, but some of the important ones are: one, by looking at a spreadsheet of data, it's very difficult to say what is the quality of our data. And when I say a quality, are there anomalies that exist within the data which they ought not to be there? Are there pieces of data which are missing completely in the data set? And what do we do about those pieces of data? So a snapshot of quality can be obtained by using descriptive statistics, and we need to have certain correction strategies which we shall look at in a subsequent time. The second important aspect of descriptive statistics is to understand the data with the help of domain knowledge to really decide on what are the appropriate statistical models that we can employ on this particular data set, and the variables that we want to use in the model. Different statistical models make assumptions about what the data types are, what the data characteristics are, and a choice of a model, one of the first steps in the choice of a model is really the types of data and the characteristics of the data. So the descriptive statistics provides those information which helps an individual to choose an appropriate statistical model and specify the model. The third area is really knowing how the data looks and knowing the characteristics of data. It helps you interpret the outputs of a model to a more action orientation. A lot of times we're not doing this for fun. I mean, we are doing this with a purpose in mind, and we have certain definitive action plan, action that we want to take. So that requires interpretation of the outputs of the model. So knowing what the data is and the relationships that exist within the data helps us better arrive at the action points and better interpret the data. So to begin, the first step is, now when we have data like this, we see that there are price, there is vehicle type, and not all pieces of data have the same characteristics. So let me explain what I feel. So the price is something which is in units, which is in dollars. So you have 4,450, 13,299, etc., etc. So as you can see that it can take any value, any real value. It can't be a negative value. It can be 0, but even 0 is an acceptable value. But there is no restriction on this particular type of data, and it can take any value in the real domain. Look at the data on vehicle type. The vehicle type has got only a few specific types. It's a limousine or an SUV or a bus or a small car. So there are only specific values that the vehicle type can take. This is to start with, this is not numeric data. So this is a text data, and it is also limited by the number of choices that can appear within this data variable. The year of registration obviously is the year. We know that automobiles did not exist at certain points in time, so it cannot, so the limitation comes in from, it cannot have dates like 1800, etc., because the concept of automobiles did not exist at that point in time. The gearbox can take only 2 values, manual or an automatic. The power PS is more like the price. It can take a continuous value, etc., etc. So the data are of different types. So let's understand what are the different types of data by understanding what are the characteristics of each of the data. All what you are seeing on your screen are all data. So when there's a football match happening and there's a jersey number, the jersey number indicates a particular person. So jersey number 10 is so and so player, jersey number 11 is a particular player, etc., etc. And then you have, let's say in the second case, you have a milometer reading, which says what is the speed at which the particular automobile is traveling, or temperature, or a podium where clearly that there is somebody who is a winner and somebody who has got the second prize and the third prize, etc. Or the marks that you get in your examination, or a survey scale which says that, you know, how do you feel about a particular issue, whether you strongly agree, disagree, or not at all agree. Currency, simple measures like a length of a piece of metal, the weight of a piece of metal, the time, or a position of a coach in a railway carriage. So all these are data. Let's look at some characteristics of these data. So the first characteristic is that all data have a characteristics of description. That is, each piece of data has got a unique label and it describes something. So if you are a student, you are given a roll number and the roll number describes you. So it says that if the roll number is 79136, it means it's a particular person. If the roll number is 79136CH, it means that you are a particular individual who is in the chemical engineering department. Yeah. Or if you are an employee in an organization, your employee number clearly corresponding. So there's a one-to-one correspondence between the value of the data and an individual. So like you have a distance, so you know a 3 feet clearly describes something, 37 degrees Celsius describes something, $100,000 describes something. So description is the first basic characteristics that a data possesses. The second characteristics is a characteristics of an order. So not only is a piece of data can indicate a description, but it can also indicate whether that number can be characterized as greater than, less than, better than, etc. So when you have two cylindrical pieces measured, one of them is 6 inches and the other one is 3 inches, you know that the 6 inches is greater than the 3 inches. So the scale of length possesses the characteristics of an order. So is it in the case of a podium. So the person who's standing on the first place has done something better than the person who's in the second place. But let's take the case of the jersey number. In the case of jersey number, there is no realistic ordering between the various jersey number. Can we say something about the jersey number 10 and jersey number 11? We really cannot. We cannot say somebody is greater than, lesser than, better than. So those comparative descriptors cannot be used with some kinds of data. One of the classical example is gender. So you have men and women, but there's no superiority or inferiority which is inferred from the piece of data itself. So that piece of data has got the characteristics of a description, but it does not possess the characteristics of an order. So the third characteristics is really the distance. So not only are we able to say one is greater than or lesser than or better than or poorer than, but we are also able to quantify the difference. So the absolute difference between the scale descriptors are known and it can be expressed in certain units. So when two cylindrical pieces are measured, one of them is 6 inches and the other one is 3 inches, we can say the one which measured 6 inches is greater and it's greater by 3 inches. And so is the case with the temperature, which says that if there are two different temperature measurements, one of them is 40 degrees Celsius and the other one is 37 degrees Celsius, we know that one of them is 3 degrees Celsius higher compared to the other one. Obviously we cannot say the same thing between jersey number 11 and 10, we can't quantify and say this is one better. Same is the case with a kind of a survey scale. We know that agree is a better state of mind compared to disagree, but we cannot quantify the difference between the state of mind in an agree and a disagree. And the same case with the podium, because the minute you have got it as a ranked data, So you know that somebody who's first has done better than the second, but how much better is difficult to quantify. So it's possible that it's a kind of a podium in a 100-meter race, and the Usain Bolt has run it in 9.78. The second person has run it in 10 seconds, and the third person has run it in 10.03 seconds. So the difference in the time gap between the first and second could be vastly different between the difference in the time gap between 2 and 3. If you are making the measurement in terms of the times measured, then the distances between the values are measurable. But if we only have a podium snapshot, we can only say that a person 1 has run it better than the person 2 and faster than the person 3, but we cannot say how much faster. The fourth characteristics is really the characteristics of origin. It's a slightly difficult concept, but essentially that there's a concept of a true zero. I think a simple way to understand this is if I convert the units of length into any unit, then the differences can still be expressed as a ratio. So the difference between 6 inches and 3 inches is, let's say, one of them is twice as long as the other. Now you convert this into feet or you convert this into centimeters, that relationship still holds, and still the object A is twice as long as the object B. The same thing is in currency. The reason why we can do this and do the multiplication between two variable values is because they have a true origin. So there is a 0. So there is a 0 centimeter is equal to a 0 feet is equal to 0 inches. Similarly, $0 is equal to 0 euro is equal to 0 rupees. Therefore, so there is a true 0 that's defined. The issue with temperature is, all we know is that that's an arbitrary 0. 0 degrees Celsius is not equal to 0 degree Fahrenheit. Therefore, if a particular measurement is made, so in centigrades, so there's a 74 degrees Celsius and 37 degrees Celsius, we cannot say that it's twice as hot, because if you convert this into Fahrenheit, then the ratio will not still be 2. Yeah. So as we notice that in description we can perform very little mathematical operations. When it comes to ordering, we can say that there is an order, but we still can't quantify the differences, so still there are no mathematical operations possible. When it comes to the third scale, which is when the third characteristics, so when you have the characteristics of distance, you can measure differences between variables, the values of the variables. And when you have the characteristics of origin, you can start performing divisions and multiplications. So the presence or absence of these characteristics determine what is the type of data. So there are 4 normal types of data. There are many classifications of types of data. What we are seeing here is what is called the Stevens classifications, which gets popularly used across the different domains. So there are 4 different types of data: nominal, ordinal, interval and ratio. We will look at what characteristics each of them have, but just before that, there are multiple terminologies that you will encounter in data science. So the nominal and ordinal data are also called categorical data. They are also many a times termed as non-metric or qualitative data. The interval and ratio scale data are called continuous or metric or quantitative data. So these are some of the other terminologies that you will encounter in the literature of data science. So the nominal data has got the property of description, but does not have the order, distance and origin. So let's look at the jersey number. Yes, it has got 9, 10, so it describes a person, but stops at that. You can, as we saw, that it does not have any order, it does not have distance, it does not have origin. Or a position of a coach, the Calais coach 12, it says that, listen, it appears that that's a coach that you need to get into if you have a ticket which says you are booked in coach number 12, but it says nothing about whether 12 is inferior to or superior to 11 and 10, etc. So the permissible statistics in this type of a scale, or you can compute the percentage. So if you have gender in a group of people, you had 70 men and 30 women. So you can say that 70% of the population is men, and you can also compute mode. We will look at what mode is in a little while. The inferential statistics, that is, if you want to generalize it to the population, you will use chi-square and binomial tests. So these are the tests that are appropriate. Again, we will look at it when we look at the inferential statistics more in detail. The ordinal scale or the ordinal data has description and order, but does not have distance and origin. So the podium that we talked about, not only do we know that there is a first position and second position, but we know that the first position is better than the second position. Or if you are an engineering student, you will have come across this Mohs hardness scale, which characterizes the hardness of different elements. So you know the talc is the flimsiest, and the diamond is the hardest. But gypsum comes in as twice, but there's nothing which tells you about, is the distance between talc and gypsum the same as the distance between gypsum and calcite? No, it isn't. Yeah. So the ordering is fixed, so you know one is superior to the other, but you do not know by how much. So the descriptive statistics that you can use is median and the percentile, so the 90th percentile, so the new element falls in the 90th percentile or the 85th percentile, etc. And the inferential statistics that you could use are rank order correlations, ANOVA. The third scale is really the interval scale, and this scale has description, order and distance, but does not have origin. So it's got an arbitrary origin, therefore you cannot perform the divisions between data pieces. Items like temperature, survey scales sometimes is assumed to be in this possessing this particular characteristics. The permissible statistics here are, you can compute the range, which is min and max difference, the mean, which is an arithmetic average, and the standard deviation. And the inferential statistics tools that you can use are related to product moments. The very superior scale, because you could perform many operations on this, is the ratio scale, which has got all the four properties of description, order, distance and origin. So currency, measurements of length, measurements of weight, a lot of physical measurements actually go into this realm because they are all very well defined and they are not arbitrarily origin based. The permissible statistics here are in addition to the mean and the median, etc., geometric mean and harmonic mean. So you can actually compute something called let's say the CAGR, compounded annual growth rates, or you can do a harmonic mean, that is you can actually get a mean value of rates. So a particular, let's say a car traveled between A and B at a speed of 60 kilometers per hour and returned at a 40 kilometers per hour rate. What's the average speed? So we will require an harmonic mean computation to do this. So all these are possible when the scale type is ratio, and the inferential statistics has got coefficient of variation. So as you notice that as the scale order goes higher, starting from nominal to ordinal, the range of mathematical operations that we can perform also keeps increasing. So whatever you can do in the nominal scale, you can also do it in the interval scale or the ratio scale, but not vice versa. So I cannot employ a geometric mean into a nominal data, but I can employ the mode and percentages in the ratio scale data. So let's get back to the data that we have and look at with what we have learned is, can we typify these data? So we can obviously see that there are quite a few pieces of data which are ratio. So you have price as a ratio scale data, so it does not have an arbitrary origin. So you can actually say that one car is quoted twice as much as the other car in terms of price, or one car's power output is 3 times as much as another car's power output. So the minute you can do that and it's correct, so that's a ratio scale data. You also have kilometers run, which is a ratio scale data. Let's look at the year of registration. The year of registration, though it's put in numeric value, I cannot say 2005 is 1.13 times 1999. So that mathematical operation makes no sense on a year of registration, but the distances are similar. The distance between 2003 and 2004 is similar to the distance between 2006 and 2005, which is a 1 year gap. So that's more of an interval scale data is what we have. The vehicle types, the gearbox, and whether there is a damage to the car are all just nominal data. So you have in vehicle types, you have limousine, SUV, bus, etc. So there are many categories under this particular nominal variable. So it's not necessary that a nominal variable needs to take only 2 values, like a gender, say men and women. It can take multiple categories. So then the vehicle type has got lots of categories. The gearbox type has got only 2 categories, manual and automatic, and the damage also has got only 2 categories, yes or no. Why is all this important? Is because the type of data determines the kind of measures that we can use from statistics in describing the data. The type of data also determines the kind of statistical models that we can employ when we want to understand the relationships between the different variables.